So today, guys, we're going to talk about arcs and chords. How are arcs of circles measured in relation to central angles? Apply properties of arcs and properties of chords. Our key terms are central angle, arc, minor arc, major arc, semicircle, adjacent arc, and congruent arc. Alright, moving on. Alright, guys, a central angle is an angle whose vertex is the center of the circle. An arc is an unbroken part of the circle consisting of 2 points, called the endpoints, and all the points on the circle between them. What? Yep. Circles have things that we call central angles. Okay? Anytime two radii meet, they form a central angle. Whoa, that's really off. I'll get out your way in a second. The whole thing. Yep. So in this case, look at this circle up here. Angle B is called a central angle. Okay? It's an angle whose vertex is the center of the circle. There's a dot right there in the center. That's angle B. Or we would call it angle ABC or CBA. You can learn it that way, and that's no problem. Anytime you have angles that form at the center of the circle, they're going to be central angles. If you want a practical definition, here it is. Anytime two radii meet, they form a central angle. What are the radii here? AB and CB. They meet and they form angle B. How about it? An arc is an unbroken part of a circle consisting of 2 points called the endpoints and all the points on the circle between them. It's a really fancy way of saying this, y'all. If I went from A to C along the rim of the circle, that would be the arc. Arc AC, okay, is simply the part of the circle that goes right there. If you want to think about it like a pizza, the crust of the pizza is the arc. Okay? All of you had pizza, right? Okay. There's one really important relationship you need to know, and that's this. Central angles and arcs that create them are congruent. So if this angle is 50 degrees, arc AC is 50 degrees. Let's move on. Right, a minor arc is an arc whose points are on the interior of a central angle. Measure of a minor arc is equal to the measure of its central angle. Thank you. Write down major arc and semicircle too. Yes. Minor arcs. Major arc is an arc whose points are on or in the exterior of a central angle, and endpoint of an arc lie on a diameter. They are called a semicircle. All right, real quick. Major versus minor arc. Really, really simple, actually. Okay. Look at AC. What is the most direct route from A to C? Is it going counterclockwise or clockwise? It's going clockwise. Okay? It goes clockwise. Yeah. Let me do this way. A to C. Would taking the green route or the blue route get there quicker? The blue route. That's the minor arc. The longer way to go is the what? Major arc. That's the only difference, guys. And most of the time, check it out. Most of the time with a major arc, you're still going from A to C, right? But notice what's the difference between how the minor arc is written and the major arc. There's what? There's one more point or letter, right? And that's how you'll know if it's a minor or a major arc. So if you see just 2 letters, minor arc. Major arc, though, major arc is going to go through several different letters. That's probably not a great textbook definition. That's the practical definition. Okay? Semicircle. Semicircle, aka half of the circle. Which brings me to a good point. How many degrees are in every circle? 360 degrees. Which means how many degrees would be in a semicircle? 180, which is how much of that? Half. Very good. Okay?
Hard.
Incredibly difficult so far. Should be an easy day, hopefully. 30 seconds up.
Do I get an extra day to do that? Yeah, let me.
No, you don't. You can turn in late, though. All right, circle graph shows the types of grass planted in the yards of one neighborhood. Find the measure of arc KLF. First off, major or minor arc? You know right off bat.
It's a major.
Major arc. How many letters are there?
3.
3. Second off, let me tell you something right here, okay? All right, guys. In this part of the country, I'd go with Bermuda or Zoysia, okay? We're in that lower Piedmont region, okay? You might get some fescue, although it's probably, I mean, most of the time it survives the summer, but Bermuda is pretty much the grass of choice around here, okay? Do not plant centipede grass. Don't plant centipede, all right? It's going to die in the southern, number one, it's going to die in the clayish soil that we have, okay? Number two, it's probably going to die in the heat that we have, so you're either going to end up having a water bill that's astronomical, or it's just going to be way too much heat for it to stand, okay? So I'm just letting you know right now, okay? Go with the Bermuda. It's really simple. It'll take a few years for it to come in, but it will come in eventually, okay? Anyway, what we're doing here is all that they do is they take 360, and you're going to subtract out how many degrees there are involved in the I think they did this through KJF. Yeah, they took out all of this part and said whatever's left over is the measure of that arc. Really, this is just an exercise in determining how many percentages of 360 you have, okay? Don't worry about that one so much. This is more of what you're going to be used to, okay? All right? So, first thing you would do, I would tell you to do this. Take all of those percentages, switch them all to degrees. How do you do that? What is 0.25? 0.25 times 360. How much is that? 90 degrees, right? 0.25 times 360. That means that the angle measurement and the arc that creates it is 90 degrees. Okay? Their question said, what would be the measure of angle FMC? FMC, that's going to be 9%, 10%, and 11%. You can add up the percentages, 9 plus 10 plus 11, you're going to get 30. What is 30% of 360? Do what? 30% of 360. 108. Did you do it, or did you just randomly look at the board?
I actually did it.
Alright, won't be bad today. Alright, the adjacent arcs. Okay, adjacent arcs are arcs of the same circle that intersect at exactly one point. Arc RS and arc ST are adjacent arcs. The reason adjacent arcs are important is all because of our arc addition postulate. The measure of an arc formed by two adjacent arcs is the sum of the measure of the two arcs. Okay? Let's kind of make our way through this real quick. It should be really common sense, guys. If you go from RS and then you go from ST, you really have two arcs, right? You have arc RS and then you have arc ST. The arc addition postulate just says this. Yeah, but if I went all the way from R to T, that'd be like adding together arc RS and arc ST. That's all you're doing. Just like the angle addition postulate. You added together the angle measurements to get a bigger angle measurement. Same principle here. Okay? Exact same principle. Really, really simple, common sense stuff. Okay, let's move on. Let's put this into practice here. Find the measure of arc BD. Question: if it says the measure of arc BD, is it talking about the minor arc or the major arc? Eh? Minor, right? 2 letters involved. So if you look at BD, is this telling you to go the long way or the short way? Short way. Okay? Got me? Should be pretty simple by now. You'll start seeing what this is in just a little bit. Couple ways to do this. The way I recommend is this. Let's just figure out what the total measurement would be of the angle involved there. BFD, that whole angle measurement, okay? And it's like a puzzle putting it together, but it's an easy puzzle. Do I have any diameters in this circle?
Yeah.
What are they?
BE and AC.
BE and AC are diameters, right? Okay. Diameters have how many degrees on them? 180, because they are semicircles, right? They're semicircles, so they have 180 degrees. So, guess what game we're going to play? We're going to play the game where we take 180 and we subtract out the angle measurements we're given. 97.4 and 52. That leaves me with 30.6. Okay? So the measure of CFD is 30.6 degrees. All right? Now,
Yeah, 52 and 36. Take that out.
okay, so 2 ways I could do this, right? I could go, okay, now I want 180 minus 52 and 30.6. What does that give you? 97.4. Okay? That would be correct. You said 97.4. The other way you could do it is use your definitions. Guys, are those vertical angles? Are vertical angles congruent? Yeah. Okay? Last step involved. Take the total measurement of 97.4 and 30.6. You get 128. See how I told you it's a puzzle, but it's an easy puzzle, right? You're using 360 and 180 on pretty much every problem so far. Okay? And that's really what you're going to be doing over and over and over again. Okay? Alright, here's another example. JKL. Okay? JKL. Now, in this circle, okay, JKL, is that the minor or major arc?
Wait, say it again?
Is that the minor or the major arc, JKL?
That's major.
Yeah.
Yeah.
It's really the minor arc,
All the way around.
because the major arc would incorporate going further around the circle, right? It's got 3 letters, right?
No.
I wouldn't want to do this to you, okay? I want to keep it simple. If they do this, is it really gonna screw you up that bad? No. Why? You go from J to K, K to L, right? Come on.
You gotta do that.
Come on. That's pretty easy, right? How do they do this one? Well, KPN is a diameter, and JPM is also a diameter. Pretty simple start. This is 25 degrees. Okay? 25 degrees here. Tyler, if this total has to be 180, how can I find what KPL? How can I find that missing piece? Perfect. Subtract it all from 180, you get 115. Now to figure out how much JKL is, just add 25 and 115. That's how you get 140. Any questions so far? It's been pretty easy, right? Pretty easy. Pretty good so far. Okay. Alright. LJN. L to J to N, you do the same thing. I think you guys are getting the hang of it. Okay? Alright. Within a circle or congruent circles, congruent arcs are two arcs that have the same measurement. So it's possible to have congruent arcs in a circle. Arcs that have the exact same measurement. We've already seen that a couple times. Those vertical angles that existed earlier, right? They would have congruent angles, and the congruent angles, if they're central angles, produce congruent arcs.
You know, there's actually a problem with people matching the suit on them.
So
Ugh.
we get to this theorem or sets of theorems. You don't have to write all this down so long as you listen. Alright. In a circle or congruent circles, congruent central angles have congruent chords. Congruent chords have congruent arcs, and congruent arcs have congruent central angles. Ms. Miller, I know that anxiously anticipating the highlights to come. You're not getting highlights? What are those things called? Oh, okay. If I have congruent central arcs, is there such a thing as a congruent central arc? No, there's not.
No, no.
Because they're called congruent central angles.
Cool.
Congruent central angles have congruent chords. Congruent chords have congruent arcs. Congruent arcs have congruent central angles. I should be way past this. Guys, if they're congruent, are they equal? Yes. Okay, so it's real simple. Okay? If they're congruent, they're equal. So are these congruent chords? Yes. If they're congruent chords, would they have congruent arcs? Yes. So if they have congruent arcs, set the arcs equal to each other, solve for your missing variable, and you'll figure out what your missing arc measurement is. Okay? It's just a rehash of everything with congruency. I spent 6 weeks really emphasizing it. By now, you should pick it up. Congruent, set things equal to each other and solve. Go with me? All right. I got one more important thing that we got to get down. You definitely should write these down. Okay? You know what? I'll be nice. You don't have to write them down. I got one example that you must write down. Okay? All right. Just read it for me. In a circle, if a radius or diameter is perpendicular to a chord, then it bisects a chord in its arc. And in a circle, the perpendicular bisector of a chord is a radius or a diameter. Here's the types of problems that you're going to see. Just like this. You need to write this down. Alright, guys, this problem is something that I'm going to show you a lot over the next 5 weeks, okay? Because it's pretty much always on the EOC, right? They like to put this problem on here because, as you can probably tell, the Pythagorean theorem is involved, right? It goes back to something that I said Tuesday, which I told you I would probably say every day. All radii are created equal, okay? Is R to M a radius? Is this a radius? Yes. How much is R to M? No. R to M is what? 17. How am I getting 17? How about 8 plus 9? Okay? I'll say it again. All radius are created equal. If I go from R to N, is that a radius? Yeah. What would be the distance of R to N? Okay, if I go to R to P, is that a radius? What would be its distance? Okay, you'll notice that it's got the 90-degree angle there. If this is a radius, it's a line, and if it's a line, that means it's got to have 180 degrees on it. If it has 180 degrees on it, and 90 are on one side, that means 90 are on the other. Okay? This sets up the Pythagorean theorem, right? The question says find n to p. So in the end, I want to find this entire distance. Okay? I'm going to break that problem up. I'm going to use the Pythagorean theorem and double my answer. So, if I went from N, let's call this point, let's call it Z, okay? Let's call that point Z, okay? If I go to N to Z, that's what X is going to equal. And then, if I go to Z to P, that's what X is going to equal, okay? Which means N to P is going to be X plus X, or 2 times X, right? We can set up our Pythagorean theorem here. X squared, 8 squared, 17 squared, X squared, 64, 296. Subtract 64. X squared is 225. Square root that, you get 15. Is your final answer 15? No, I can't emphasize this enough, guys. 15 only gets you halfway, right? Remember, you want the entire distance from N to P. So 15 times 2, or 15 plus 15, yeah, that's your answer that you're looking for, okay? With me on that? Right? If you wrote down this problem, it's a really good one. It, goes through everything. You're gonna see that problem over and over and over. I'm gonna put it on the quiz. I'm gonna put it on homeworks. I'm gonna put it on EOC reviews. It's gonna be on your unit test. It's gonna be on the EOC, okay? And you can see at first glance it's pretty tough. Once you do it 2 or 3 times, it's an easy problem, okay? Follow with me?